Welcome back. Today we're doing Leetcode problem 155, min stack. Today I'm wearing a headband because I'm feeling athletic while I sit in front of a computer and code. Okay. So let's get into it. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement the class. So here we can see min stack initializes stack object, push pushes an element val onto the stack, pop removes the element on the top of the stack, top gets the top element of the stack, and get min retrieves the minimum element of the stack. And you must implement a solution with O of 1 constant time complexity for each function. Let's look at an example, right? Let me move this over here. So, let's look through this explanation here. This is, to me, it's easier to read than this input-output. We have an empty stack, we initialize it, we push -2 on, push 0, push -3. Get min returns -3 because this is the smallest, the minimum of the three values that we've pushed onto our stack. We pop from our stack, and then we check the top of the stack, which is 0. And the reason is because we popped this -3. And then we call on get min, and we see that it's actually -2. So if we were going to do this problem, and let's just first ignore the kind of constraint here, right? Let's ignore the time constraint of having to access everything in O of 1 time. Let's kind of go through an example. Well, before that, let's just talk about how we would do it otherwise. And I think it's pretty straightforward. You just use a stack, and if you're going to do this the brute force way of getting the min, when you call on this get min function down here, you would just loop through everything in your stack, and you're going to look for the smallest value, but that would take O of n time each time, and that's really bad. And so that would be the brute force solution. Also, it says here that methods pop, top, and get min will always be called on non-empty stacks. So that's good to know. It makes our life a little bit easier. The approach that we're going to do here, and let's talk about it in this kind of diagram. Let me move this over. Is we're going to use actually 2 stacks. There's probably, well, it's not probably, I know there's a different way to do this where you actually use 1 stack and then you just used a minimum element variable, but honestly, when I see this problem, I've seen this problem in the past in an interview, I just jump straight to go to the brute force solution, talk about that for a second, and then I just move to this one because honestly this one just makes the most sense to me. And the other one is fine, but I just have a small brain. Okay, so let's kind of go through why we're using 2 stacks. The main stack here in our problem is going to actually just take care of all the values that we're pushing onto the stack. So main stack is going to take care of push, pop, and top, right? Ignore get min right now. If it was just those 3 functions, to push a value on, to pop a value off, and to check what the top value is, a regular stack just does the job. And the reason we're using a min stack is to take care of that remaining problem, right? Knowing what the minimum value is at any point in time. And the way that we're going to do it is anytime we push an element onto, we call a push, we're going to push onto our main stack and to our min stack a new value, but we're only going to push onto the min stack the smaller of the top value on the min stack and the value we're going to push on. Well, let me go through an example, right? So let's say this is the commands that the operations that we received. Push a -2, right? So when we push a -2, our stack is going to look like this. There's nothing on here. We're just going to push -2, right? There's nothing to consider. both stacks are empty. You're just gonna push. Then we push a 0. Okay, we push a 0 onto our main stack. When we push onto our min stack, what are we gonna do? And I think this is a good place to pause. What we're gonna do is we're actually gonna take the minimum between this value 0 and this -2, and that's what we're gonna push onto our min stack, right? So we're gonna push the minimum of our min stack, what was at the top, and our value, like that, right? We're gonna take the minimum between min stack at the very last thing we added in, which is -2, and our value, which is 0. And you're gonna see that -2 is the smaller of the two values. So we're gonna push onto the min stack, not 0, but -2. This way, this min stack is always going to keep track of the minimum value seen up to this point. We push a -3 on in the next operation. We check here the minimum between the last element in our min stack, the top of our min stack, and -3. -3 is smaller than -2, so we would push here a -3, not a -2. And finally, we push a 4. 4 is obviously not smaller than -3, so we still push a -3. And let's say now we start to pop off, and then we call on get min. Let's say that the next operation we do, let me write it here, is a pop, and then a top. Sorry, get min, right? Let me move this down a little bit. So here, if we pop, let's make this red. If we pop off our main stack, sorry, not pop off the main stack, but if we just pop, we would remove this 4. And when we pop, we also remove this entry. That's actually not true. We don't remove that. Do we? Yes, we do. We want to keep it symmetrical, right? We want to have the same, always gonna have the same amount of elements in the main stack and the min stack. The second pop, we remove a -3. We remove this -3. And when you call get min at this point, well, then you would refer to the top of the min stack, and your min value would be -2, and that would be correct. So that's why we're going to use two different stacks. So let's go ahead and implement this. So I call mine main stack and a min stack, and what I'm going to do is I'm just going to use two different lists in Python. They behave in a way that's basically like a stack, depending on how you treat them. So when we push onto our when we call in a push operation, right, the first thing we're going to do is we know that no matter what, we're going to push onto the main stack. So we're going to append this value onto the main stack. Now we're going to consider the min stack. There's two cases, right? Either there is nothing on the min stack, or there is something on the min stack. So if the length of our min stack is equal to 0, then we're just going to push append onto our min stack the value. Else, we're going to append the smaller of the two values. So this append function here is actually going to take the minimum between the most recent smallest value on the min stack, which is the last thing, and the value that we want to push. So that should be it. Now when we pop, we're just going to remove from both the min stack and the main stack, not the main stack. Okay. And for top, we're just going to return the main stack we're returning the topmost element of the stack. And then get min, well, we're also just returning the min stack, the topmost element of the min stack, right? Because it keeps track, like we said. So let's run this, see if it works. Nice. Great. So yeah, this solution runs in, all of the operations run in O of 1 time, or constant time. We are using extra space by using not just one stack, but 2 stacks. And like I said earlier, there are definitely ways to do this with just 1 stack. But to me, this is the clearest way. Honestly, like, I'm not going to spend too much time on trying to figure out the math. I think, like, if you're doing this problem and you get it during an interview and you give this solution, it's a great one. But they also honestly might ask you, like, okay, how do you improve upon this? And if you think about it a little bit, yeah, you'll probably be able to figure out a better solution. But for me, I think the important point is to understand this concept of, well, like, let's keep it simple. And yeah, right.